This is every electric vehicle broken down. Most explainer videos tell you an EV has a battery and a motor. That's not wrong. It's just missing about 90% of the picture. A modern electric vehicle is a coordinated system of 6 major subsystems. And understanding how they interact is the difference between owning a black box and actually knowing what you're driving. In this video, we're going to walk through all 6. We'll keep it visual. We'll keep it accurate. And by the end, you'll understand why every design decision, from Tesla's tabless cells to Hyundai's 800-volt architecture, actually makes sense. Let's start with the obvious one. System 1, the battery pack. The battery pack is the largest, heaviest, and most expensive component of an EV, typically between 350 and 700 kilograms, about a fifth to a third of the entire vehicle weight. But calling it a battery is like calling your house a building. Inside the pack, you have 3 nested levels of structure. Cells, the smallest unit, could be cylindrical like Tesla's 4680, prismatic like BYD's Blade, or pouch like in a Hyundai Ioniq 5. Modules, groups of cells wired together, typically 12 to 24 cells per module, arranged in series and parallel to hit the target voltage and capacity. And the pack itself, the modules plus the structural casing, plus the cooling system, plus the battery management system. Here's a key insight. In newer designs, like Tesla's structural pack and BYD's Blade architecture, the module layer is disappearing. Cells are integrated directly into the pack, saving weight, space, and assembly cost. This is called cell-to-pack, or CTP design. It's the single biggest structural innovation in EV batteries this decade. System 2, the electric motors. An EV can have 1 motor, 2 motors, 3 motors, or even 4. But almost all of them fall into 2 families. Permanent manier synchronous motors. Used in the Tesla Model 3 and Y, the Ioniq 5, the Mach-E, and most modern EVs. Higher efficiency, especially at low speeds. The downside? They need rare earth magnets, which are expensive and geopolitically complicated. AC induction motors. What Tesla originally used in the Model S and X. No magnets needed. Slightly less efficient at low speeds, but they handle high load conditions extraordinarily well. Tesla often pairs both. An induction motor at the front, a permanent magnet at the rear. To get the best of both worlds, the motor doesn't directly drive the wheels. It connects through a single speed reduction gearbox, typically a ratio of around 9:1. Yes, just 1 gear. EV motors generate full torque from 0 RPM, so they don't need a multi-speed transmission like a combustion car. This is part of why EVs feel so different to drive. It's also why they have so few moving parts compared to a combustion engine, and why, mechanically, they're far more reliable. But that simplicity is deceptive. The complexity moves somewhere else. Software. System 3. The inverter. Here's a component you'll almost never see mentioned in reviews, but it's arguably the most engineering-dense part of an EV. Your battery stores DC, direct current, but your motor needs AC, alternating current. Specifically, a precisely timed 3-phase AC, with frequency and amplitude varying every millisecond based on how fast you want to go. The inverter is what makes that conversion, and it does it tens of thousands of times per second. Modern inverters use silicon carbide MOSFETs, a recent shift from older silicon IGBTs. Why does this matter? Silicon carbide handles higher voltages and switches faster, which means less heat, less wasted energy, and more range from the same battery. This is the single component that improved most dramatically in the last 5 years. It's also one of the most common failure points. When an EV has a sudden reduced power warning, the inverter is the prime suspect. We'll do a full deep dive on inverters in a future video. For now, just remember, it's the brain of the powertrain. System 4, the battery management system. Every single cell in your pack, That's between 4,000 and 8,000 individual cells in a Tesla. Needs to be monitored. The battery management system tracks voltage, temperature, and current draw from each module, sometimes from each cell. It actively balances cells, predicts state of charge, manages charging speed, and crucially, disconnects the pack if anything goes wrong. When you read, "My Leaf battery degraded 30% in 5 years," versus "My Tesla's battery is at 92% after 200,000 miles," you're almost entirely looking at differences in BMS sophistication. The chemistry is similar. The management is not. This is also where most software updates land. When Tesla pushes an over-the-air update that changes your charging behavior, that's the BMS being reconfigured remotely. System 5. Thermal management. EV components hate heat. They also hate cold. Keeping everything in a narrow operating window is the job of the thermal management system. Most modern EVs run liquid coolant loops, typically a glycol mixture, through the battery pack, the motors, and the cabin heater. The most efficient systems use a heat pump, which can move heat from one subsystem to another rather than generating new heat from scratch. When you hear people complain about EV range dropping 30% in winter, this is usually why. The heat pump struggles below freezing, and the car has to use resistive heating, which is dramatically less efficient. Tesla's octovalve in the Model Y is a famous example of integrated thermal design. One valve assembly routes coolant through 8 different paths, depending on what the car needs. It's elegant engineering. System 6. The 12-volt system. Last and least glamorous. The 12-volt system. Yes, your high-tech 800-volt EV still has a humble 12-volt battery in it. Why? Because every accessory in your car, the door locks, the wipers, the radio, the airbag controller, even the contactors that connect the high-voltage pack, were designed for the 12-volt automotive standard. Replacing all of that is more trouble than just keeping the 12-volt around. The 12-volt battery is the most common failure point in modern EVs. It's also the one that strands you the most embarrassingly, because if it dies, you can't even unlock the car to access the high-voltage system. Tesla recently moved to a lithium-ion 12-volt battery to fix the chronic failures. Other manufacturers are following. This is also a perfect example of a theme we'll come back to repeatedly on this channel. The most modern car still carries decisions made by automotive engineers 50 years ago. Here's something I want to point out, because I think it gets missed a lot. When people talk about EVs being simpler than combustion cars, they're not wrong about the mechanical part. But the complexity hasn't disappeared. It's moved into the software, the BMS, the power electronics, the thermal system. This is why a misdiagnosed inverter fault could be a $5,000 mistake, while a similar fault in a combustion car would be a sensor swap. We're not driving simpler cars. We're driving differently complex cars. And understanding that difference is what this channel is about. So to recap, every modern EV has 6 major systems. 1. The battery pack, with cells, modules, and the BMS. 2. The motors, almost always permanent magnet or induction. 3. The inverter, doing thousands of DC to AC conversions per second. 4. The BMS, the brain that keeps the pack alive. 5. The thermal management system, often with a heat pump. And 6. The humble 12-volt battery, that legacy nobody can quite get rid of. In the videos to come, we'll dive deep into each one. Failure modes, design decisions, repair realities. If you want to actually understand your EV instead of guessing, subscribe and see you Wednesday. And if you found this useful, drop a comment with which subsystem you want covered first. I'll be reading.